So we've seen that at least under the quadratic programming formulation for both the hard margin and soft margin versions of this large margin classifier, the input data enters into both the optimization and the prediction only in the form of pairwise inner products. These inner products serve as a kind of similarity metric, looking at how close one sample is to another. Loosely, the classification boundary depends only on the small subset of classes that are most similar, given that they are of opposing classes. The same criteria would apply under any basis expansion. Fitting in the expanded transformed space would still depend only on the most similar subset of oppositely labelled vectors. And so it would depend only on this inner product similarity metric. If we have some basis expansion phi, where phi is a transform that turns any input vector x into the x in the expanded space, x prime. So it might consist of a whole bunch of different functions, one for each of the expanded dimensions. If we have such a transformation and can find another function, which is known as a kernel, which looks like this, which given any two of the original vectors can compute a value which would be given by the dot product of the expanded vectors, then we can substitute that kernel function both in the prediction and fitting functions in place of the explicit calculation of dot products. So the fitting function would look like this, and the prediction function like this. Now, it's not immediately obvious why we would want to do such a thing. But note that k, our kernel, is a scalar function that just takes two vectors of dimension d and produces a single scalar value. Phi, on the other hand, is a vector function. It takes a vector of dimension d and projects it into a space where it's of some other dimension, let's say m. And quite often, m will be much bigger than d. And even once you've projected into that dimension, you still have to compute the inner product there. So potentially, using the kernel function could bypass a lot of that process and save a lot of computational work. Given that we're discussing this at all in these lectures, it probably will come as no surprise that this is in fact the case. There are useful kernel functions that allow us to sidestep the projection into a very high dimensional, even infinite dimensional transformed basis and bypass that and just compute the dot product in that space directly. This is known as the kernel trick. And it makes it possible to fit our linear soft margin boundaries in arbitrarily high dimensional or even infinite dimensional spaces, but do so in a way that is computationally feasible. So let's look at a couple of important and popular cases. If we look at this kernel function here, k of u v equals 1 plus u dot v to the p, it turns out that this is equivalent to expanding into a basis of all monomial combinations of all the features in each vector up to a degree of p. There are some scaling coefficients on the different terms, but we don't particularly need to worry about that at the moment. So let's consider a very simple example where d, our input dimension, is 2, and p, our monomial degree, is also 2. In this case, kuv is this expression here, 1 plus u1 v1 plus u2 v2, all of that squared. If we expand that, we get this quite big expression, 1 plus 2 u1v1 plus 2 u2v2 plus u1v1 squared plus u2v2 squared plus 2 u1 u2 v1 v2. So this is a bit of a mouthful, but note that in each of the terms in this expression, it's just matching terms in u multiplied by matching terms in v. So we can factorize this into a dot product of two vectors, one that is entirely from u and the other that is entirely from v. In other words, our kernel K is equivalent to calculating the dot product of phi of u dotted with phi of v, where phi is this transformation here. A similar expansion holds for any choice of d and p, but obviously the size of these expanded monomial vectors gets very big very quickly, and the algebra becomes kind of unwieldy. The thing to note is that k, our kernel function, is approximately OD. It requires only the dot product in the original feature space, whereas phi is roughly OD to the power of p, which is potentially an awful lot. So there's scope for an enormous saving here. Another common and important kernel function is the radial basis or Gaussian kernel, which looks like this. This is commonly expressed with two different parameterizations, one in terms of gamma and the other in terms of sigma, where gamma is equal to 1 over 2 sigma squared. The sigma formulation makes it look more like a traditional Gaussian bell curve, and the sigma parameter can be understood as the standard deviation of that bell. It turns out that this kernel is equivalent to expanding into an infinite dimensional basis, a basis consisting of all possible monomial combinations of the features of the vector, with rapidly reducing coefficients, obviously, so that the eventual series converges. Applying phi, the transformation, into the new basis is literally impossible in this case, and yet the kernel function is really quite compact and efficient. The radial basis kernel is best understood as a similarity metric. If u and v are very similar, then u minus v will be close to 0 and the exponential will be close to 1. If u and v are very different, then u minus v might be huge and the exponential will be close to 0. The hyperparameter gamma or sigma governs how steeply this similarity metric drops off with distance. This Gaussian or radial basis kernel can fit almost arbitrarily complicated decision boundaries in its infinite expansion space. We'll look at a few examples in the next section of the lecture. It raises the question, though, if we can use that similarity metric, can we use any similarity metric that we like? What is required for any function that we choose to be a valid kernel function that we can apply the kernel trick with? Well, a kernel is only valid if the assumption that we made to begin with holds true. That is to say that k of u and v is equal to phi u dot phi v for some transformation phi. In other words, it has to define a genuine inner product in some vector space. It turns out that for this to be the case, the gram matrix, when applying the kernel to data, also known as the kernel matrix, has to be positive semi-definite. So you may have encountered the gram matrix before. It's just the matrix of pairwise inner products between all of the vectors in a data set. For an ordinary dot product, using our row-wise formulation of the design matrix, The Gram matrix in that case would be X times X transpose. This is more often phrased as X transpose X using column-wise vectors. For the kinds of generalized inner products we're talking about being represented by our kernel, the Gram matrix will look like this. Again, it's just all of the pairs passed through the kernel function packed into a matrix. So it turns out that if that kernel matrix is positive semi-definite, then the kernel is a valid kernel, and the quadratic programming problem specified for our soft margin classifier can be solved using that kernel. If it's not, it's not. It's an if and only if requirement. This is known as Mercer's condition. It's a slightly special case of a more general theorem known as Mercer's theorem. Strictly speaking, this requirement that the kernel matrix is positive semi-definite should hold for any given data. However, it is also possible that you can have a kernel which produces a positive semi-definite matrix for some data that you're interested in, even though it wouldn't necessarily do so for all cases. In this case, the kernel matrix is known as conditional positive semi-definite, and the QP problem can still be solved here, and you can still get away with using it, even though, strictly speaking, the kernel isn't valid. As well as greatly improved computational efficiency in high-dimensional spaces, kernels also allow us to define inner products for kinds of data that they wouldn't normally apply to. You can define kernels that perform a similarity matrix that acts as an inner product for things like text, for sequences, trees, and graphs. This effectively allows learning algorithms that support the kernel trick, such as support vector machines, to be used directly on data types that they otherwise might not be able to, without first having to construct some embedding into a real valued vector space. An embedding is still conceptually there, but the kernel allows you to bypass ever actually computing it. The kernel trick is not limited to support vector machines. It can be applied to any learning algorithm in which the data, the inputs, can be confined to pairwise dot products. It turns out that this is true of many of the learning algorithms that we've looked at so far, including linear and ridge regression, logistic regression, k-nearest neighbors, and the perceptron. It can also be applied to some algorithms that we will look at later in the module, like principal components analysis. However, SVMs really are the canonical example of a kernel learning algorithm, and they're probably the way in which people most commonly encounter kernels.